So here we are, continuing on our DNA replication journey. We've talked about how DNA polymerase is only going to be able to move in the 3' to 5' direction. So while down here, as helicase unzips the DNA polymerase here can add bases continuously because we're moving in that 3' to 5' direction. But DNA polymerase has to always move from 3' to 5'. So that's to the right on this top strand. So helicase has unzipped up to this point here. DNA polymerase attaches and moves to the right. While it's moving to the right, DNA helicase, if I was like pinching DNA helicase, while this DNA polymerase is moving to the right, DNA helicase is unzipping further down the DNA. When DNA polymerase says, oh, wait a minute, I'm done here, but I have more to do, it can detach, move over, get closer to that helicase, and start moving down in the 3' to 5' direction again. So while for the continuous strand, we can just move straight up, the discontinuous strand is going to make chunks. So now what we're going to do is work on a sketch that will explain that without having my hands all up in your face. So let's get started. I'm going to draw a replication fork, fancy name for what we just looked at. We're going to have 2 strands, DNA. I'm going to put my DNA helicase here. I'm going to say the DNA helicase is going to be moving down that way. I'll label it just in case. Just in case, get it? Ha ha ha. But down here, the helicase has not reached these bases yet, so they are still connected together by hydrogen bonds. Helicase has already unzipped up through here and up to this point. So these bases are not connected to one another with hydrogen bonds. Our directionality of our DNA strands again, so over here I had 3', across from 3' is going to be 5'. 3' to 5', across from a 5' is going to be 3'. What's going to happen when we get this DNA polymerase is that it's going to click down onto the 3' end of our DNA, and it's going to start adding bases while moving up the DNA strand. So because this is already unzipped, perfect amount of space for DNA polymerase to click in and add some more bases as it goes. So for this example, I'm going to write in bases. A, T, C, G, and so on. As this DNA polymerase comes and sits on this single strand DNA at the 3' end, it's going to overlap that T, that thymine. And while it's doing that, it's going to sit there and wait for an adenine to come in and hydrogen bond to this thymine. And it's going to facilitate that action. So DNA polymerase has successfully gotten the adenine to be attached to the thymine. Once that happens, it's going to move down and do the same thing for this adenine, and it's going to have a thymine coming in, and then it will also connect to this adenine. So now DNA polymerase has successfully added 2 complementary bases. It's going to continue along and do the same thing for the next bases in the sequence. So it's going to add a C to the G, a G to the C, an A to the T, and so on. I'm not going to have our DNA polymerase do all of them so we can still see what's going on. But I will do these for us. So based on what we know about base pairing, C's go with G's, G's go with C's, A's go with T's, and T's go with A's. And give them their hydrogen bonds to let them attach together. And here we have represented our growing continuous strand. So this is called our continuous or our leading strand. We call it leading strand because it goes faster and it leads the way for DNA replication. This strand up here, where we have discontinuous movement of the DNA polymerase, that's going to be called our lagging strand. The reason it's called the lagging strand is because DNA polymerase can only move from 3' to 5'. So for this strand, DNA polymerase does it in chunks. So it adds complementary bases in chunks. So just to have things cleaned up a bit, we're going to make a new sketch for the lagging strand.